course, we did that 8 times, so here's the rest of the chart filled in. You can see the moles of sodium carbonate is going to be the same for the first 4 because I had the same volume of sodium carbonate for the first 4, and then it's going to be 2.5 times bigger for the second 4 because I used 2.5 times as much of the solution. Moles of NaHCl is always going to be twice the moles of the sodium carbonate, so you can see the first 4 the same and the second 4 the same. The volume of HCl added was what I gave you, so you got around 24 cubic centimeters for the first set and then about 60 for the second set, and just doing the calculation to get the concentration of HCl from each of those. There are the values, check them yourselves as you see fit, and we're going to average those out, 0.0868 molar, because none of these really was out of whack at all. Do the post-lab questions. Concentrated sulfuric acid, concentration 80.4 moles per cubic decimeter. Describe how to make 250 cubic centimeters of a 2 molar solution of H2SO4. In other words, what volume of concentrated sulfuric acid contains the same number of moles as 250 cubic centimeters of a 2 molar solution of sulfuric acid. So we're going to use our dilution equation. Let's make some pretty colors here. I want the volume of the concentrated acid, the 18.4, that will have the same number of moles as the 250 cubic centimeters, that's V2, of the 2 molar diluted concentration of H2SO4. Throw in the numbers and we get V1 is 27.2 cubic centimeters. So I'm going to need to take 27.2 cubic centimeters of concentrated sulfuric acid, which I will measure out using a pipette. I'll add that to some water in the appropriate volumetric flask, the 250 cubic centimeter volumetric flask, and then I'll add water up to the line of that volumetric flask. Why does the procedure specify anhydrous sodium carbonate? Because if we got waters of hydration associated with this, while the bottle might say 1 water or 2 waters or whatever the case may be, that water of hydration is a variable number. It's relatively easy to lose a few waters. And so because therefore we don't know the real composition of the hydrated sodium carbonate, we can't get the exact molar mass, and so we can't convert the mass to moles. So I showed you in the pH curve, it's a dibasic substance, can react with 2 equivalents of acid. Why didn't we not use the volume at the first equivalence point in the calculation? In other words, the volume of HCl needed to turn all the carbonate into the hydrogen carbonate. 2 reasons. First of all, the volume at the first equivalence point was half the volume to the second equivalence point. We can only measure volume on a burette to within 0.05 cubic centimeters, and so the percentage of error in a smaller volume is greater than the percentage of error in a bigger volume. So as I said earlier, you always want to have the bigger volumes possible within, of course, experimental limits and cost limits and so forth. Then the second thing, if you think about what that curve looked like, it was very wishy-washy at the first one, but then with the second one it plummeted on down, and so much easier to determine an endpoint that is nice sharp endpoint instead of one that kind of meanders into the equivalence point / end point. What's methyl orange? What's the structure? Look it up. It's a nice diazo salt. Then you hit organic chemistry in year 13. You'll learn that these type things here are diazos. They're very nice colors, nice range of colors associated with whatever you have on these benzene rings that are attached to the diazo group. Another indicator would be suitable for the standardization where we want it to change color in the same range at about 3 to 6 pH. And if you look up, bromophenol blue is suitable for that, and Congo red is suitable for that. Different indicators change color at different pH ranges. Bromophenol blue and Congo red change at about the same pH range as methyl orange. And finally, what was the concentration of the HCl solution? Well, we used the average value that we just determined, 0.0868 moles per cubic decimeter.